No, I get it.
Right, so now I'm going to look a little bit more about the uranium series isotopes. And I sort of mentioned that in the first lecture. They were sort of put up in that table of other isotopes. There was uranium and thorium there as well. But they differ a little bit from other isotope systems. So when we were looking at sort of the rubidium strontium system, samarium, neodymium, potassium argon, basically you just went straight from rubidium to strontium, one step. Straight from samarium to neodymium, one step. Straight from potassium to argon, just one step. However, when we look at the uranium series, this also applies to thorium, let's look at the second, what we see is that there are a whole bunch of steps. So if we go take uranium-238, then initially we get alpha decay to thorium-234. You can see the mass number drops by 4. Then we go from thorium-234 to protactinium-234. That's beta decay. The mass number doesn't change, even though the element changes. Back to uranium, so this time uranium-234. Then we go to thorium-230, radium-226, then radon-222. And there's a couple of typos I realised when I was looking through this morning. So when it's in this, when I go to uranium-235, I'll come to those in a second. But anyway, get to radon-222, which is a gas. Then polonium-218, astatine-218, radon-218, polonium-214, lead-210, bismuth-210, polonium-210, and finally I get to lead-206. So there's a lot of steps there. And you see exactly, sort of similar when we go to the uranium-235. There are a lot of steps there. We go through a lot of beta and alpha decay steps before we finally get to our lead isotope, which is stable and doesn't undergo any further radioactive decay. So each of these steps involves moving to a different element on each step. And each of those elements has different geochemical properties. So the typos are, I think in your note, this is just 219 radium, should be 219 radon, and I think this one is listed as 215 actinium, and it should be 215 astatine. So a couple of small typos will make a huge difference. Okay, so we go through these different elements, and when we're going from uranium all the way down to lead, we're going through a whole range of different elements. And some of those elements are radically different in how they behave. So, uranium, for example, is relatively soluble in oxidizing conditions, but very insoluble in reducing conditions. Protactinium, thorium, actinium, polonium, bismuth, they're very sort of insoluble, very sort of unreactive in many ways. Radon, we know out here, is a gas, noble gas. It really doesn't want to sit in the crystal lattice. If it can get out, it will do. And we have radium, is one of the alkali earth elements. It's not as soluble as the alkali elements, but still, relatively soluble. And thallium, which actually appears as part of the thorium decay scheme, is also fairly soluble. So all these elements have different geochemical properties. Now, if we look at, again, this decay scheme again, okay, so if we take uranium then, 238 again, it's got a half-life about roughly the same age as the age of the Earth. And it decays to thorium-234. Well, thorium-234, 24-day half-life, it's, not going to stick around for very long. We get down to protactinium 234, it's got an even shorter half-life, only 6.5 hours. So there isn't really time for those two isotopes to express their different geochemical behaviour. We get to uranium-234, we're back to another uranium, so fairly similar behaviour to the parent uranium isotope. Then we get to thorium-230, well, it's got a half-life of 75,000 years. So it actually is hanging around long enough that it can start to express a slightly different geochemical behaviour. The other thing that's happening is each of these alpha decays, remember, involves a helium atom being emitted from the nucleus. So in the decay scheme of uranium-238 to lead-206, there are going to be 8 helium atoms kicked out of the nucleus. So that's 8 times we're firing a mini cannonball out into the lattice. And so 8 times we're causing damage to the lattice around our original uranium atom. So we're causing a lot of damage. And some of these isotopes would quite like not to be associated with uranium. They've got different geochemical behaviour. They don't sit in that sort of, if they sit in the mineral, they don't sit in that lattice particularly easily. And so they like to escape. And if they escape, obviously, then that's going to change how we calculate ages. And we see a similar thing for thorium-232. It's also sort of included, tends to be included with the uranium series, because it's got a long half-life. In this case, actually about sort of 3 times the age of the Earth. And it also goes through a whole series of decay steps and also producing more helium-4. So again, all these intermediate isotopes, we're creating something which could escape. Well, actually, in the case of thorium-232, all these intermediate isotopes have very short half-lives, so we don't have to worry so much there. But when we go back to the uranium, some of these have got long half-lives, thousands of years. So there's a chance for them to express their different geochemical behaviour. Okay, so we could write decay schemes like this. So remember, this is the one for strontium. The strontium isotope ratio we measured today, the one we started, equals the one we started out with, plus parent as a reference isotope times e to the lambda t. We could do exactly the same for the 2 uranium isotopes and the thorium isotope. Whoops, this one, bottom one, oh sorry, no, I have it right there. So top one is the thorium, 232 thorium became ultimately lead-208. So I could write that sort of decay scheme, whereby the lead-208 over 204 ratio, 204 lead is a reference isotope that we measured today, is equal to the one we started out with, plus 232 thorium, parent isotope, divided by 204 lead, a reference isotope, times e to lambda t minus 1. I could do that for decay 232 thorium to 208 lead, 235 uranium to 207 lead, and 238 uranium to 206 lead. However, because there are all these multiple steps, lots of helium damage to the lattice, lots of opportunity for elements to escape, the intermediate isotopes, then when I plot up isochron diagrams for these systems, what you tend to get is quite messy isochrons, with the ratios not defining a really strong linear isochron. Oh, just one point though, if you're a bit confused by going through all of these, what you will see is that there are no isotopes that appear in different chains. All the isotopes are unique to that individual chain. I don't expect you to remember all of these. I can't, so let's see why you should. However, if you're a bit confused about which lead isotopes comes from which parent, remember that the mass number has to change by a multiple of 4, corresponding to helium-4s. So if we're going from 238 uranium to lead-206, the difference in mass number is 32, 238 minus 206, so hence 4 heliums kicked out. 235 going to lead-207, difference of mass number is 28, 7 heliums kicked out, and when we go from thorium-232 to lead-208, that's a difference of 24, so 6 heliums kicked out. So that all those 3 decay schemes are unique. There's no crossover, no isotope appears in more than one chain. Okay, so this doesn't really work very well for a way of using lead to date minerals. Except there's a few mineral phases which are very resistant to losing in their intermediate isotopes. The most important one of these is zircon. So zircon is what this formula here, zircon silicate. It doesn't form a major part of rocks, and it only crystallizes really from sort of in the continental crustal type rocks. But it has 2 characteristics that make it very useful for dating. The first is that it contains very high concentrations of uranium when it first forms, because uranium can substitute quite nicely for zircon. But it contains very low concentrations of lead, because lead doesn't fit into that lattice very easily. So that makes it actually easier when we're using it to calculate ages, because we don't really have to worry about too much inherited lead. The other most important thing is that zircon is what we call a very refractory mineral. That means once we've made it, it is really hard to destroy it. To give you an indication, you can have, so what we might have is a granite melt. We crystallize a zircon grain from there. Let's say that granite then comes to the surface and it gets eroded. The soluble elements like rubidium, potassium will dissolve, they'll go down the river out to the ocean. You'll get left behind, some minerals will be converted to clays, make up the soil we see, accumulate sediments, but the zircon doesn't dissolve. The zircon stays as a zircon crystal. So our granite erodes away, forms a sediment. The zircon grains get carried with the sediment into a sedimentary basin. Over many millions of years, that sedimentary basin may be buried, may be heated up by some tectonic event, and those sediments may melt. If those sediments melt, they can form another granite. That granite would be what we call an S-type granite, formed from melting sediments. However, the original zircon stays the same. So that zircon is now in a completely new granite, but it still retains the age information from the first granite that it formed from. So zircons are extremely robust. Once you've made them, they really can hang on to their ages very well. And so they've been very useful for dating, for example, the formation of the crust, because even though the original rock has gone, the zircon stayed behind. So we can measure the ages of zircons we find in sediments or in younger granites, and we can get the ages that crust originally formed up. So let's see how this works. Okay, so we can write out this decay schemes I said for uranium-235 and uranium-238. Incidentally, the zircon doesn't really contain any thorium, so we don't need to worry about that. It contains uranium. I mentioned it doesn't start out with any radiogenic lead, any inherited lead. So it's a little bit like when I was talking about the potassium argon system. So these equations simplify a bit because there's essentially no 204 lead to start off with. So we can simplify these equations so that the 207 lead in our zircon crystal is simply equal to 235 uranium, which expressed times e to lambda T minus 1. I put lambda 235 and lambda 238 just to indicate that there are different lambda values for uranium-235 and uranium-238. They've got different half-lives, different lambda values. So we can rearrange those equations such that the 207 lead over 235 uranium ratio is equal to e to lambda T minus 1, and the 206 over 238 uranium ratio is equal to e to lambda T minus 1 with the appropriate lambda values. So if we make a plot of these two lead uranium ratios against one another, this is what we end up with. So on the y-axis we've got lead 206 over 238 uranium, and on the x-axis we've got lead 207 over uranium 235. So we start off at 0. No lead, but uranium. We start off at 0. After half a billion years, beg your pardon, we would have grown in this amount of lead 206, this amount of lead 207. And each tick mark here shows how the lead 206 to uranium 238 and the lead 207 to uranium 235 ratio has changed. So, if we formed the zircon 4.5 billion years ago, it would now have a ratio up here. Now this line is curved because these two uranium isotopes have different half-lives. So they don't grow in at the same rate. The lead 206 doesn't grow in at the same rate as the lead 207. And this line is called the concordian. It's called the concordian. That's quite important. Okay, so this is how things would grow over time. Now, I said that zircon is very robust, but even zircon has its weaknesses. So let's say we have a zircon crystal that formed 4 billion years ago, and the rock that it was contained within experienced some high temperature metamorphic event 3 billion years ago. Then, if we look at that system 3 billion years ago, this is the plot we would see. So it would have started out here and got to here. Let's say we have some heating event. It could be that the granite is completely eroded, that zircon is now in some sediments, those sediments have been remelted to form a new granite, or it could be that simply that granite has been heated up a lot. So what happens when you heat up a zircon? If you heat it up enough, the lattice expands, and because, as I mentioned, lead doesn't really sit happily in the zircon lattice, that lead can start to diffuse out. Now, it's not like argon, which will just zoom out at the first sort of gentle warming of a rock. You have to heat the zircon up pretty high, and the lead diffuses out quite slowly. Nevertheless, we can lose some lead. Now, if we lost all the lead, this point, we heat it up, we lost all the lead, we just go back to 0. If we didn't lose any lead, we'd sit here. So if we then looked at that rock system today, if we hadn't lost any lead, the zircon would have quite happily gone up to here. If we lost all the lead, then we record an age of 3 billion years. However, in a lot of cases we lose some of the lead. Now, although the lead isotopes grow in at different rates, because the half-lives of the two uranium parent isotopes are different, when you lose lead, the rate at which you lose lead depends solely on the chemical properties of lead. And lead 206 has exactly the same chemical properties as lead 207, lead 208, and lead 204. So they grow in at different rates, but they do fuse out at exactly the same rate. So what that means is that they would go back towards the origin on this straight line. We lose half the lead 207, then the 207-235 ratio drops by a half. And then that would also mean that the lead 206 to uranium 238 ratio will also drop by a half. So when we lose part of the lead, we now fall on this straight line here. Okay, so now the rock cools down again, the lead's trapped again. What will happen then is each of these three different points, they might be sort of small, medium, large size zircons which have lost more or less lead, or they might be the inner and outer parts of an individual zircon grain. Anyway, they will lie on this line here. Once the zircon cools, the lattice contracts, lead can no longer escape, and then these points here start to grow lead again. And they move on a line which is parallel to our original Concordia. And they remain on this straight line which is called the discoid. So, this is what it would have looked like 3 billion years ago. We run the clock forward 3 billion years, and this is what it looks like today. So if we now measure the lead-uranium ratios in that zircon crystal, they now lie on this straight line. Where that straight line, the upper part intersects the Concordia, gives the original age of the zircon. Where they intersect the lower part on the Concordia gives us when we had the metamorphic age. Most cases we're interested in the original crystallization age. Some applications we may be interested in the metamorphic age, but other isotopes are probably better at giving us a metamorphic age of the rock. And this could be, as I said, this could be a zircon crystal which formed in a granite 4 billion years ago. That granite lifted to the surface, completely destroyed, completely eroded away. That zircon crystal that sort of tumbled down a stream and has been trapped in a sedimentary basin. Those sediments have been heated up, and 3 billion years ago they heated up to form a new granite. So this lower age could actually represent a formation age of the new granite. But the zircons would still contain some information about when they first formed. So a huge amount of work has been done on dating zircons. And it's almost like an industrial scale process. People will go out to sedimentary basins, which are sort of draining large areas of the continent, and they'll collect tons and tons of sedimentary rock and crush it up. And zircon's quite heavy minerals, quite dense, and so you can use some heavy liquids to separate out the zircons. Then all those zircon grains are separated out and mounted on a like a thin section, and they're analysed by an ion probe in this sort of instruments like this. This is called what's called a shrimp, which stands for sector high resolution ion microprobe. They would typically, these sorts of instruments would typically cost anything between £4 and £5 million. So they're really expensive. We don't have one here, not many labs do, but really expensive. But you can actually analyse lots of zircons using a machine like this, and hundreds of thousands of zircons have been measured. And so people make these plots like this, where you get some data points, you extrapolate the straight line, and where it hits the Concordia gives you the original age of your zircon. And the oldest zircons that have been found, and it's sort of, it's almost like a sort of competition to who can find the oldest zircons. The oldest zircons that can be found have ages of a little bit over 4.3 billion years. And bearing in mind what I said is, the Earth is about 4.55 billion years. Zircons form in continental crust. This suggests that some continental crust was forming on the Earth within 250 million years from when the Earth first formed. I'd say that the very old zircons Okay, the zircons have an age of 4.3 billion years. Actually, the sedimentary rocks that they're sitting in were only got an age of about 2.5 billion years. So again, the zircons can record really old ages. And in the practical bit, you will do a calculation. Okay, so what else can we use uranium series dating for? Okay, we can also take advantage of the fact that there are these different geochemical states. So we've talked about that uranium is relatively soluble in seawater as uranium carbon. Okay, so if we take this uranium-238 case, let's say we've got some uranium-238 happily dissolved in seawater. First step, it decays to thorium-234. Well, thorium is much more insoluble than uranium, and it has a sort of an average residence time in seawater dissolved form of only about 300 years before it is removed with iron manganese oxides and it's incorporated in an iron manganese oxide rich sediments. Whereas uranium has a residence time of the order of a billion years or so. So the first step, we get to thorium-234. Pretty insoluble, but it's only got a half-life of 24 days. So the chances are it's not going to precipitate out solution before it decays to protactinium-234. Well, protactinium is also pretty insoluble, but it's only got a half-life of 6.5 hours or so. So again, it hasn't got time to precipitate before it decays to uranium-234. Well, that's got a half-life of about 250,000 years. It's quite happy sitting in seawater. And then it decays to thorium-230. Well, thorium-230 has a half-life of 75,000 years. So bearing in mind that the thorium atom sitting in seawater only lasts in its dissolved state for about 300 years, there's plenty of time for that to be precipitated out from seawater before it then decays to radium-226. So, what does that happen there? Okay, so what happens then is this 230 thorium precipitates out from seawater and accumulates in iron and manganese oxide. And when it gets to that iron and manganese oxide, it's what we call unsupported. And what we mean by that is that when we were in a zircon grain, when that 230 thorium decayed to 226 radium, it was replaced fairly soon afterwards by another 234 uranium decay. However, if it's precipitated out into this iron and manganese oxide, well, the uranium isn't precipitated out. That's quite happy being sitting in seawater. It's soluble. So there is no uranium-234 in those iron and manganese oxides to replace the 230 thorium as it decays. It's what we call an unsupported isotope. So remember our decay equation, that number of atoms we see today is equal to the number we started off with times e to the minus lambda t. So in this case, if we're looking at some iron and manganese oxide, then the amount of 230 thorium we see in those iron and manganese oxides today is equal to the amount I started off with times e to the minus lambda t. Now, as I said, we like to measure ratios. So 232 thorium is radioactive, but it's got a very long half-life, about 14 billion years. So effectively, we can treat it as a stable reference isotope in this case. So if we measure now the 230-232 thorium ratio, then that's going to be equal to this value here. Okay, so we can apply